So, you see a self-driving car glide by, and you have to wonder, right? What is actually going on inside its brain? How does it see a stop sign, figure out what to do, and then actually hit the brakes? It's definitely not magic, so let's dive in and unpack the incredible engineering behind a digital driver.
First things first, why are we even doing all of this? It really boils down to this one number. Over 90% of all accidents on the road are caused by us, by human factors. We get tired, we look at our phones, we just make mistakes. The entire point of autonomous driving is to build a driver that just doesn't.
So the goal here is to create what you could call a perfect digital driver, an AI that's been designed from the ground up to completely bypass our human flaws. An AI that never gets tired, never gets distracted, and has this constant 360-degree view of everything happening around it all the time. And this right here is the core logic behind the whole thing. It's a simple but brilliant continuous loop that's happening thousands of times every single second. The car senses the world, then it thinks about every possible move and picks the absolute best one, and finally it acts, controlling the steering, brakes, and gas. This sense, think, act loop, that is the foundation for everything we're about to get into. Okay, so let's start with the first step in that loop: sense. Before a car can do anything at all, it has to see what's going on around it. It needs eyes, but not just any eyes. It needs a kind of superhuman vision.
So the car's primary eyes are cameras. They give it rich, high-resolution color vision, kind of like our own eyes. They're awesome for spotting things like traffic signs or lane markings. But a lot of systems also use LiDAR, which is super cool. It shoots out pulses of laser light to build this incredibly precise 3D map of its surroundings, day or night.
But here's the key thing to get. No single sensor is perfect. You really have to think of it like a team of specialists. Cameras are amazing at recognizing stuff, but, they can get totally blinded by sun glare or darkness. Radar works in any weather, which is great, but it's not so good at telling a person from a lamppost. And LiDAR gives you that perfect 3D picture, but it can struggle in heavy rain or fog.
So how do engineers get around these individual weaknesses? Well, they use a really clever technique called sensor fusion. The car's brain takes all the data streams from all the sensors, the cameras, the LiDAR, the radar, and fuses them all together. This creates one single, unified, and way more reliable picture of the world than any one sensor could ever hope to provide on its own. It's pretty genius.
All right, so the car has gathered all this data from the world around it. Now it's time for part 2. Think. We need a brain powerful enough to actually make sense of all that information, and it has to do it in real time.
Your standard desktop computer CPU just isn't going to cut it here. We're talking about processing gigabytes of data every single second. It's an insane amount of information. That's why these cars use highly specialized hardware, custom-built chips that are designed for the kind of massive parallel processing that AI needs. This processing unit, it really is the core of the car's brain. And this brain has a few key components. First up, you've got the image signal processor, or ISP. Honestly, the best way to think of this is like a pair of built-in polarized sunglasses for the AI. It takes the raw, often messy video feed and cleans it right up. It corrects for sun glare, it brightens up dark shadows, because without this, the AI would be trying to make life-or-death decisions based on a really crummy picture.
Okay, so once the image is clean, it gets handed off to the Neural Processing Unit, or NPU. This is the AI's intuition. This is the part that scans that clean image and starts recognizing patterns, figuring out that, hey, that cluster of pixels over there has a 99% chance of being a pedestrian, and that other shape is a bicycle.
And then there's what might just be the most important part of the whole system, the safety island. Think of this as the AI's reflexes. It's a completely separate, tiny little computer that has only one job: watch the main AI. If that main system ever glitches, freezes, or crashes for any reason, this chip's job is to immediately take control and safely stop the car. It's the ultimate failsafe.
So the car sees the world. It understands what's in it. We're still in the think phase, but now it has to actually make a decision. Where do we go from here? This part is all about planning the perfect path forward.
From the AI's point of view, the world looks a lot like this grid. It's basically a map with a starting point, an end point, and a bunch of obstacles that absolutely cannot drive through. So the fundamental problem it's trying to solve is finding the safest, most efficient path from the green square to the red one. It's a classic problem in computer science.
To solve this puzzle, it uses a famous algorithm called A*, which you see in everything from robotics to video games. The logic is actually beautifully simple. First, it identifies all the obstacles, the black squares. Then it scores every possible next move it could make, the yellow squares. To be efficient, it ignores any squares it's already looked at. And finally, it just picks the move with the lowest cost. It's that simple.
But what does cost actually mean here? Well, it's not just about the shortest distance. The AI uses something called a cost function, which acts like a really strict judge with a penalty system. Driving perfectly in your lane? That's 0 penalty points. Good job. But braking really hard gets you a small penalty. Turning a corner too sharply? That's a medium penalty. And hitting a curb? Oh, that's a huge penalty. So the AI's goal is to find the path with the lowest total penalty score, which makes sure the ride isn't just fast, but also comfortable and, most importantly, safe.
Okay, so the brain has done all the math, it's calculated that lowest cost, safest path. Now it's time for the final, critical step in our loop. Part 4, act. This is where that digital decision becomes a real, physical action. Now, for the AI to act on its decisions, it needs a totally different kind of control system. I mean, an AI can't physically press a brake pedal, right? So instead, it uses what's called drive-by-wire technology. Instead of a bunch of mechanical rods and hydraulic lines, the AI just sends electronic signals to motors that control the steering, the gas, and the brakes.
And this slide shows it perfectly. On the left, that's the old way. A physical steering column connects the wheel you're holding directly to the tires. But on the right, in the steer-by-wire system, that physical link is completely gone. It's all been replaced by sensors, motors, and electrical signals. This gives the AI incredibly precise digital control over the car. And the biggest benefit of this whole setup is just pure raw speed. The time it takes from the AI's brain deciding, I need to stop, to the brake pads actually clamping down on the rotors, it's measured in milliseconds. That's so much faster than human reflexes, and that tiny sliver of time can be the difference between a near miss and a serious accident.
So finally, let's talk about Part 5, the road ahead. Because this whole sense, think, act system isn't static. It doesn't just get installed and stay the same. It is constantly learning, constantly getting smarter, safer, and better over time. And there are 3 really cool ways this learning happens. First, engineers feed it what's called ground truth data. Think of it like millions of digital flashcards, showing it images and saying, this is a pedestrian, this is a stop sign, over and over until it gets it right 99.9% of the time. Second, it practices in these insanely realistic simulators, almost like a video game, where it can face dangerous situations thousands of times without any real-world risk. And maybe the most clever part is shadow mode. Here, the AI runs silently in the background while a human is driving, constantly making predictions about what it would do. Engineers can then compare its choices to what the human actually did, which creates this amazing feedback loop for learning. So when you really break it down into this sense, think, act loop, you start to see that this isn't magic at all. It's an incredible piece of engineering, with superhuman senses, a specialized brain that's always calculating the safest move, and reflexes that are faster than our own. It's a system designed piece by piece to be more reliable than we are. So the ultimate question really isn't about the technology anymore. It's about us. When will we be ready to trust it?